Hello. We will discuss full factorial design with single replicate. So, we are continuing with factorial design, and you have seen that in case of even two factors with n replicates. So, we require a b n this number of experimental runs. Now, it may so happen that there is resource constraint. For example, maybe if you are using raw material, maybe the batch is not sufficient enough to conduct n number of replications for a b experimental different settings. So, or you have time constraint, or you have financial constraint. So, all those things, the resource constraint will put things differently, and maybe you will go for a n equal to 1, that is known as single replicate. Or it may so happen that you don't have any other option other than going for single replicate, because more than one is not available. Maybe somebody else has done replication this experiment, or many things. So, ultimately what I mean to say here, that there will be situations when you have to deal with full factorial experiments with single replicate. So, what will happen under such situation, and what kind of analysis, statistical analysis possible, that is what will be discussed in this lecture. So, full factorial design with single replicate, then we will show you a special test known as Tukey test for interactions. This is very important, and then I will show you one example, and we will explain with example that how you will analyze the experimental data, that is full factorial experimental data with single replications. What I am assuming that you all know the, and mu y I j is mu plus tau I plus beta j plus tau beta I j plus epsilon I j. This is what is the fixed effect model, and in last lecture we have estimated these parameters with n replicates. So, also in last to last lecture what happened, we have seen that ANOVA analysis of variance, and to find out the effect of all those parameters, and then we have accepted or rejected the null hypothesis for related to factor A, related to factor B, related to their interactions. Here when we don't have replications, or we have only single replicate, then the problem is the error variance will not be estimable. Tau beta I j, that is the interaction, and the experimental error cannot be separated. So, that means error this cannot be estimable because of this thing, that error and these are together confounded kind of thing. It cannot be separated. There are no tests on main effects unless the interaction effects become 0. So, if there is no interaction present, then what happen? We put this equal to 0, and tau beta I j, when put equal to 0, the equation become like this. So, let me repeat this one. Full factorial design with two factors a and b, y I j k we use, that is mu plus tau I plus beta j plus tau beta I j plus epsilon I j k. Now, k stands for replications. If n equal to 1, we do not require this term. So, our observation will be y j, y I j will be mu plus tau I plus beta j plus tau beta I j plus epsilon I j. Okay. So, under such situation, if we use this full model, what happened, because we have only n equal to a b number of observations, this put restriction on estimation of sigma square, which is basically MAC, error estimate value is MAC. Second is that this tau beta I j, this one, and the error component, they will be inseparable. So, unless the interaction is 0, so you cannot go for this kind, you have to go for more, that means n equal to more than 1, that is what is the issue. So, that means when we can use, if tau beta the interaction is 0, then you can go for single replications. If interaction is 0, then what will happen, this y I j equal to mu plus tau I plus beta j plus epsilon I j. So, this will be our model, I equal to 1 to A, j equal to 1 to B. So, when you do factorial experiments and you are dealing with single replication, then please keep in mind that interaction effects will become 0, and that means you have to test whether interaction effect is there or not. If you find the interaction effect is there, then you cannot deal with this, you have to go for more number of replications. So, if interaction effect is 0, then your model will become simpler, and you have to have a test of no interaction. This test is known as Tukey's test, Tukey's Tukey's test of non-additivity or test of interaction. Here what happened, what is our H0? H0 is that tau beta I j, this equal to 0, and H1 is tau beta I j not equal to 0. This is for all I j combination, and this is for at least one I j combination. So, here in Tukey's test, what happened, you have to test this. Tukey says that this tau beta I j, this can be thought of gamma, a constant, into tau I into beta j. Then you put in the equation, original equation, y I j equal to mu plus tau I plus beta j plus gamma tau I beta j plus epsilon I j, because this is what is equal to tau beta I j. Then you find out the error SSE. SSE will be sum total I equal to j equal to 1 to b, I equal to 1 to a, then epsilon I j square, which is nothing but sum of I equal to 1 to a, j equal to 1 to b, y I j minus mu minus tau I minus beta j minus gamma tau I beta j, this square. So, what do we want? We want to know the value gamma. So, if you do derivation with respect to gamma, then what you will get? You will get 2 sum total of I equal to 1 to sum total I equal to 1 to a, j equal to 1 to b, then all those things will be there, y I minus mu minus tau I minus beta j, then what happened, this minus gamma tau I beta j, it will be there, plus this one will give you another quantity called that tau I beta j. Okay. So, this will give you plus into tau I beta j. put this to 0 and then find out gamma. Now, let us see, because this derivation will take little time. So, I have given you the way you have to do it. Let us see the second slide here. You see this become 0. You multiply all those things. So, the first quantity will be tau y beta j y I j, second one will be tau y beta j mu, third one will be tau y beta j square, tau y square beta j, fourth one will be tau y beta j square, fifth one will be gamma tau y square beta j square or tau y beta j whole square. This will become 0. Now, from this to this, what happened? This can be the second term. As there is no j, tau y is not involved with j, we can bring here, mu we can bring to the left. That means one, I just give you one symptom. For example, the second term is minus I equal to 1 to a, j equal to 1 to b, tau I, beta j and mu. So, this term mu is independent of I j, we can write minus mu sum of, now tau I is independent of j. So, we can write tau I equal to 1 to a, then also we can write j equal to 1 to b beta j. This can be written, but you all know that tau I sum and sum of beta j, they are 0. So, this quantity becomes 0. In the same manner, the third quantity, this will become 0, fourth quantity will become 0. So, we have only two quantity left, this one and this one. This cannot become 0 because y I j is multiplied here. So, this minus this, that means this minus this will be 0. So, what you are getting? You are getting gamma, equal to sum total I equal to 1 to a, j equal to 1 to b, tau I, beta j, y I j divided by sum of tau I square, sum of beta j square, I equal to 1 to a, j equal to 1 to b. Okay. So, I mean this derivative putting to 0 will give you a gamma value. Now, using this gamma value, we will calculate SSN. What is this SSN? That is sum square non-additivity n polynomial. This is basically test of interaction. So, that means it is the interaction is the tau beta I j is multiplicative with tau I and beta j, that sense it is not additive to that. So, SSN is this we have seen, because this is the interaction square sum of this. Now, tau beta I j we have considered at gamma into tau I into beta j. So, that square will be, that means gamma square tau I is beta square, this can be written like in this manner. And then gamma square value you put here, this is the gamma square value you put here. Now, tau I square beta j square, this value will be there. So, the lower portion tau I square beta j square, this is square term. So, this and this cancel out. So, in the denominator 1 tau I sum of tau I square into sum of beta j square, this will remain, and the numerator is the sum of this square, that is I equal to 1 to a, j equal to 1 to b, this square. So, what we will write this one, we know the estimated value of tau I, we also know what will be the value of beta j. So, we know y I j, it is already given. So, if you put all those values here, that estimation part, then instead of tau I you are writing y I dot bar minus y dot bar. In case of beta j you are writing y dot j minus y dot this bar, and y I j as it is you are writing. Then what you do, you manipulate, you do algebraic manipulation, and bottom hand side this is the estimate for tau I square, this is the estimate for beta j square. Okay, that you know. Okay. Now, what we have done, we have computed, we have multiplied numerator by a square b square and denominator also by a square b square. Then when the a square b square gone in within the bracket where square is there, then it is a b, and this a b we keep here, and the other two terms, one is attached with b and another one is attached with a, because we want to, we know that SSA and SSB are nothing but this is your SSA and this one is SSB. So, AB, SSA and SSB, it is coming here like this. Now, here Yij this one, now if we know that Yj equal to 1 to b, Yij is b Yi dot bar. Similarly, I equal to 1 to a, Yij is a y dot j bar. This is known to us. So, if you put here in the numerator, so that means Yij, yi dot and y dot j minus yi dot, and this quantity you will get. Okay. So, this quantity, it is just basically the all those summation kind of things and okay. So, you get from here to here, and then with the a b and other y dot j, this one, this can be further manipulated like this, and this finally result into this. So, what I mean to say here that this although the equations here looks like a very complicated one, but please then there is only algebraic manipulation there one after another. I have given all the steps. If you could not understand further, you please put your question in the discussion forum. So, if I do the algebraic manipulation, it will come like this. So, SSN equal to I equal to 1 to a, j equal to 1 to b, Yij, yi dot, y dot j minus yi double dot, SSA plus SSB plus y dot dot square by AB into square by AB SSA into SSB. This is the quantity, this is a statistic which basically tests the non-additivity, that is the interaction present or not, that sense we will use it, and this one follows chi-square distribution with 1 degree of freedom. Okay. So, SSN is computed, it is non-additivity. Now, what we have seen that this is what we have seen earlier in the derivation, Yij, yi dot this one. So, this, now our hypothesis is this, then SS error is SS residual minus SSN. You know how to compute SS residual, these are the things we have discussed earlier. So, once you know SST A and B, SS residual you will be getting from here. Now, SSN is all non-additivity part, the other part is computed. The SS residual minus SSN will give you SS error. So, now this A will calculate, you will calculate a statistics for F0, which is SSN by its degrees of freedom by SS error by 8 degrees of freedom, and then this quantity if greater than the threshold F value, then we null hypothesis will be rejected, then will be interaction will be present. Our null hypothesis is no interaction. Okay. After that, once you are satisfied with the test that no interaction is there or interaction is absent, in that case what will happen, that interaction part will go to the residual part, and you will compute the row treatment, column treatment using the traditional usual formulas. Total you compute using another formulas, and then residual or AB by subtraction, and these are the degrees of freedom. Similarly, calculate mean squares and then compute the F, and you see that whether row treatment effects are there, column treatment effects are there or not. But please remember, interaction effects you are not putting into the ANOVA, because interaction effect will not be there, and this will be, this is basically only error is there. And the expected mean square, that from theory, that means if you say that expected value of MSA will be this, expected MSB will be this, expected residual will be this, and it is expected that expected value of MSA and MSB will be more than expected value of MS residual. So, that means this added quantities, this will be this and this, this will be will be significant more than the and then this added quantity this one, and there will be significant effect. So, one example very quickly, the two factors A with 3 levels and B with 5 levels. Suppose affect the response y, we have not assumed any physical meaning to A, B and response, just for the sake of making you understand the computation part, we have chosen this example, and the analyst has observed single response, everywhere single response, and on the value of each treatment combination the experimental data is given below. So, this is a case of single replicate. Now, what you require to do? You first find out the interaction if it is there or not. Now, row total, make column total, make overall total, and then when you test the non-negativity part using this, you use this and use F0, that value is basically 0.1667, that is the sum SSN. SSN is this, SS error is this one, and you see that the F0 value SSN by degree of freedom divided by SN error by degree of freedom. So, this value is basically, and this value is this value, this divided by this value is 0.07. So, 0.07 it is insignificant value, because if you compare this with the theoretical value like F17 alpha equal to 0.05, it will be much more than 0.07. Similarly, if you compute the B's effect, this value F0 is 1.07, it is much less than the theoretical one, but A effect is significant. So, because this 5.51 is more than F27 0.05. So, A effect is significant, interaction effect is not there, and B effect is not significant. So, what we can conclude here, the factor A has significant effect on risk. Okay. So, why I have written, if you say that response is a risk response, okay, we are saying response is measures on, it is a measure of risk on 10-point scale. A and B we have not given any physical meaning, but response measure is a measure of risk on 10-point scale. Then A has no effect, A has significant effect on risk, factor B and interaction effect no significant effect on risk. Okay. So, this is what is that means factorial design with single replicates. We have used the materials of from the book of Douglas Montgomery, design analysis of experiments. Okay. So, I hope that you are in a position, to analyze field factorial design with single replicates. Okay. Thank you very much.